بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Our lecture for today will be about physiology of urinary system. The urinary system is one of the important systems of our body which act together with other systems to maintain homeostasis. Anatomically, the urinary system consists of two kidneys and two ureter, single urinary bladder and single urethra. The most important organ of this system is the kidney. Each kidney is a bean-shaped structure weighing about 150 grams. They are located on the posterior abdominal wall on each side of the vertebral column. They are extending from the level of the 12th thoracic vertebra to the 3rd lumbar vertebra. So they are protected to some extent by the lower two ribs. Kidneys located outside the peritoneal cavity, so they are usually mentioned as retroperitoneal organs. If we look to the kidney and its relation to the great vessels, you will see that the kidney receives its main blood supply by the renal arteries on the left and right, and the blood is returned, the venous blood is returned from the kidneys to the inferior vena cava via renal veins. Also, here you see the relation of the kidney with the adrenal gland, which is one of the most important endocrine glands and concerned with the many hormones will be discussed later on in physiology of endocrine system. As you see also here, the function of the kidney. One of the most important functions of the kidney is to eliminate the waste product of the metabolism, like urea, uric acid, creatinine. Kidney also play important role in regulation of the body water and electrolytes. The kidney, under certain conditions, can concentrate the urine to very high osmolality and produce very small amount of urine, especially when we are in need or in water deficiency in our body. And this is what happened to all us at the end of fasting days, especially in summer. At the same time, the kidney can produce up to 20 liters of dilute low osmolality urines when the amount of the water content in our body is too much. And this is also seen in patients with diabetes insipidus, where the subject drink large amount of the water and form dilute urine of low osmolality. Again, the kidney or the play important role in regulation of arterial pressures, arterial blood pressure, and in regulation of acid-base balance by manipulating the hydrogen and the bicarbonate ions. It is also play important role in production of erythrocyte, red blood cells, from the bone marrow by producing about 58 to 90% of the erythropoietin, the hormone which is passed from the kidney to the blood and from the blood into the bone marrow to initiate erythropoiesis. And this is why patients with chronic renal failure who fail to produce erythropoietin usually had anemia. Similarly, the kidney play important role in regulating another hormone, which is the vitamin D3. And this, as you know, very essential for bone formation, for calcium metabolism, and the deficiency of this hormone in patients again with chronic renal failure associated with the bone problems. We'll be discuss it later. If we take a close picture of the kidney and it is a cross section, you will see that the kidney is divided into two main areas: an outer cortex, which is punctate due to presence of the glomeruli of the nephrons, and an inner part which consists of a number of what is called as medullary pyramids. These pyramids, their base directed toward the cortex and their apex toward the minor calyces. If you look here, the appearance of the pyramid is striated. This is due to presence of the large number of the nephron tubules here. Again, look here, the minor calyces combined with each other to form the major calyces. The major calyces in turn combine to form the renal pelvis, which pass into the ureters, and this will be carried the urine into the urinary bladders. There are special smooth muscles in the wall of the calyces, and the ureter carry the help in pushing the urine toward the urinary bladder. Again, look to the hilum of the kidney, which is an indentation in the medial aspect of the kidney through which blood vessels, vein, arteries, ureters, lymphatics, and the nerve move in and outside the kidney. Here, another picture of the or another cross section showing to us how is the glomeruli of the nephron are located in the cortex. This is the pale area, and how the renal tubules are present in the pyramid, and this is, as I mentioned, responsible for giving the punctate appearance to the cortex and the striated appearance to the pyramid. Next, we will discuss the nephron. Each kidney, in average, contains 1 million nephrons. And as we know, the nephron are the functional unit of the kidney. The nephrons consist of two main parts. This is the nephron. One is the renal corpuscles, and the second part is the tubule. If we look to the corpuscles here, you will see that the corpuscles is content or composed of an outer Bowman capsule. This is the Bowman capsule, which is the dilated end of the renal tubules. This is the renal tubules, and this is the dilated end of the renal tubules, which encase the glomerular capillary. This is the glomerular capillary, and I will tell you how this capillary is formed and how the kidney contains two capillary bed, and this is a special character of the kidney circulation. Now, as I mentioned, the renal corpuscle consists of Bowman capsule and the glomerular capillary, while the second part, the renal tubules, consist of the following area. Number one, the proximal convoluted tubules. The second part is the loop of Henle, U-shaped loop of Henle, which consists of thin descending segment and thin ascending segment and thick ascending segment. The third part of the tubule is the distal convoluted tubules. Look here, the distal tubules come in close contact with the renal corpuscles, with the arterioles. These are the arterioles, afferent and efferent arterioles. And here is the location of the juxtaglomerular apparatus. We shall discuss this later. The distal convoluted tubules are continue to the collecting tubules. This is the collecting tubules, which collect the formed filtrate or the terminal amount of the filtrate which stay in the tubule as a urine. The collecting tubules which located in the cortex is called as the cortical collecting tubules, and the part which is present in the medulla is known as medullary collecting tubules. The collecting tubules of many nephrons combine with each other to form large collecting tubules which in turn combine to form what is called the duct of Bellini. The duct of the Bellini open at the tip of each renal pyramid into the minor calyces. Here is the tip of the pyramid, and the duct of Bellini open to the minor calyces of the kidney. If you look to the corpuscles, you will see an afferent arterioles and you will see an efferent arterioles, and in between is the glomerular capillary. Let's speak something about the blood supply of the kidney and in a summary, and we will try to explain it to you later on in details. As I mentioned, the kidneys receive, it is supplied by renal artery. The renal artery divided several times, terminating in what is known as afferent arterioles. This is the afferent arterioles, and here is the afferent arterioles. Each nephron receive an efferent arterioles. This efferent arterioles, when enter into the Bowman capsule, it will be divided to form the glomerular capillary, and here is the filtration area. The glomerular capillary is the site of filtration area in the nephrons, and it has a high hydrostatic pressure, which is about 60 millimeter mercury in comparison to 30 millimeter mercury in systemic capillary. And this high hydrostatic pressure in the glomerular capillary is one of the essential factors of filtration in the glomeruli, which is one of the basic steps of formation of urine by the kidney. After coalescing of this capillary, they form another arterioles. This is known as the efferent arterioles. The efferent arterioles, as I will discuss later on, will feed into a second group of capillary around renal tubules. We shall see it later. These known as peritubular capillaries. So, as I mentioned, we have two capillary beds, one in the glomeruli and known as glomerular capillary, and the second around the renal tubules and known as peritubular capillaries. The peritubular capillaries next will combine to form the venules, which in turn form the larger veins, and the larger veins will end in the renal vein, and the renal vein, both sides, left and right, will empty into inferior vena cava. Here is some explanation to the, look, this is the interlobular artery, give to what is known as afferent arterioles. The afferent arterioles enter into the glomerular to form the glomerular capillary. The glomerular capillary coalesce to form the efferent. Efferent means the incoming. Efferent means the outcoming or the outgoing arteries. These arterioles, the efferent arterioles, will be divided into a next group of capillaries. These are capillaries, next capillary bed known as peritubular capillary. And it has a special name in juxta medullary nephron. I will discuss it later. This peritubular capillary are end in small venules, and these will form interlobular veins. Interlobular veins then will be combined with each other, as I mentioned, until they terminate in renal vein, and renal vein in both sides terminate in the inferior vena cava. So look, there are two capillary beds in the nephrons, one in the glomeruli and known as glomerular capillary, and another around the tubules and known as peritubular capillary. Another important characteristic of the renal blood supply is that majority, more than 90% of the blood reaching the kidney each minute, which is about 1,100 ml, which is about 20% of the cardiac output, will go to the cortex. Remember, 90 to 95% of the blood flow to the kidney go to the cortex, and only about 5% will go where? Will go to the medulla, and both percentage carry significant physiological importance. Being most of them go to the cortex because the cortex contains the glomeruli, and it is the site of the filtration, and this is what our body physiology needs. And being small amount go to the medulla, This is again very essential to maintaining high osmolality in the medulla, which is one of the most important factors of the ability of our kidney to concentrate and dilute urine. These are some difference in the circulation and the blood supply of the kidney. I will mention it again. Number one, the kidney circulation or the nephron had two capillary bed, glomerular and peritubular. Number two, the hydrostatic pressure in the glomerular capillary is higher than the hydrostatic pressure in systemic capillaries. Number three, the 90% or even more of the blood supply to the kidney go to the cortex where the nephron glomeruli are present, and only 5% go to the medulla where the renal tubule are present. Here is the juxtaglomerular apparatus. Juxta in Latin means near, and as you see, this is the glomerulus and this is the juxtaglomerular apparatus. Therefore, the apparatus which are near the glomerulus. As I mentioned, this area or this structure are present in the wall of afferent arterioles and also in the wall of the distal convoluted tubules. As you remember, when we mentioned the renal tubules, I showed you how distal convoluted tubules come in close contact with the glomeruli, and especially with the afferent and efferent arterioles. The epithelial cell lining the distal convoluted tubules in this area is modified epithelial cell known as macula densa. They had the sensitivity for glomerular or for filtrate content of the sodium and even chloride, and according to this content of the filtrate from sodium and chloride, they can regulate the diameter of the afferent arterioles, and they can increase or decrease renal or glomerular blood flow. The next component of this apparatus is the juxtaglomerular cells. Juxtaglomerular cells are special modified cells in the wall of the afferent arterioles. They are concerned with secretion of a special hormone known as renal. Some physiologists add third types of cell to this apparatus, which is known as extraglomerular mesangial cells. The main function of juxtaglomerular apparatus is to regulate, as I mentioned, blood flow to the glomeruli, and accordingly it will regulate the volume of the urine output. And the second function is regulation of the renin secretion. Renin is a hormone secreted by the glomeruli and by the juxtaglomerular apparatus, and they play important role in activation of angiotensinogen into angiotensin 1. Angiotensin 1 is in turn activated into angiotensin 2 by angiotensin converting enzyme, and angiotensin 2 is the active hormone which play important role in regulating the vasoconstriction of the blood vessels. It also played important role in regulation of the sodium and the water output by the kidney, and also it play important role in stimulation aldosterone secretion and regulate thirst mechanism. We shall discuss renin, angiotensin, aldosterone system in a special lecture in the future, inshallah. The next structure we shall discuss the glomerular membrane. As I mentioned just before, the glomeruli is the site of filtration. So, across which layers the fluid from the capillary filtrate to the Bowman capsule. these layers is known as the glomerular membrane. And as you know, and it is not need to thinking about it. The wall of the capillary are lined with the fenestrated endothelium. There is a basement membrane, and this is also from the histology, you know that in every tubules in the kidney, where there is epithelial cell, there is a basement membrane. And the next layer is the epithelial cell forming the wall or the inner wall of the Bowman capsule, and this is known as podocyte. This membrane is very porous for filtration, and a tremendous amount of water and which is part of the plasma, and its content will be filtrated into the into the Bowman capsule from the glomerular capillary across this membrane. The membrane layers are negatively charged, and this negative charge play an important role in repelling the negatively charged molecules from being filtrated. One of the important molecules is the protein, especially the albumin. The size of the albumin allow it sometimes to filtrate across this membrane, but the negative charge in the membrane will repel and prevent albumin from being filtrated. And there are certain pathological conditions in which this negative charge is lost, and which is called as minimal change glomerulonephritis, and this is associated with albuminuria, which shall be discussed in pathophysiology. Now, how urine is formed. We mentioned that the blood reaches the nephron, which is the functional unit of the kidney, by afferent arterioles. After it reaches into the Bowman capsule, it will form the glomerular capillary. Here, a number of forces, hydrostatic and oncotic forces, will interact to initiate filtration. This is a passive procedure, depend on difference in pressure in between the glomerular capillary and the lumen of the Bowman capsule. This is the lumen of the where filtration takes place. So the urine formation is depend on 3 or sometimes we say 4 steps. Number 1 is the filtration, and we shall discuss it. Number 2 is tubular reabsorption. Number 3, tubular secretion, and in the final segment of the tubules there are water reabsorption. This will be depend on the osmolality and antidiuretic hormone, and will be discussed when we speak about tubular reabsorption. So, in a summary, the 3 major processes of urine formation, filtration, which take place in the glomeruli, number 2, tubular reabsorption and secretion, which take place in the tubules. Here again, you see the afferent arterioles, glomerular capillary, afferent arterioles, pretubular capillary, then to the venules. As I mentioned just now, the high hydrostatic pressure in the glomerular capillary will cause passive movement of tremendous amount of plasma, water, and content from the glomerular capillary into what? Into the Bowman capsule. This filtrate is similar in composition to the plasma, except it contains no blood cells and no protein, and also the protein binding molecules. Again, I will repeat it. The glomerular filtrate, which is a filtration from the plasma of the blood in the glomerular capillary to the Bowman capsule cavity, is similar in composition to the plasma, except it contains no blood cells, no protein, and no protein binding molecules, because their size, the size of the protein and their negative charge and the size of the red blood cells and the white blood cells prevent them from passage across or through the pores which are present in the glomerular membrane. The amount of the fluid filtered by 2 kidneys each minute is in average is about 125 ml per minute. 125 ml. The total amount per day is reached up to 180 liters. 99% of the filtered fluid and substance will be reabsorbed again to the circulation by renal tubule reabsorption, and leaving only 1.5 up to 2 liters of urine to be passed per day. Remember, every day our plasma filtrates 60 times in the nephrons of the kidney. How we measure this? The average volume of the plasma in our body is 3 liters, and the average daily filtrate is 180 liters per day. So if we divide 180 by 3, it will be 60. 60 means this 3 liters of the plasma filtrate 60 times through the nephrons every day, and this is essential to remove the waste product of metabolism and the toxic substance from our blood, which is one of the core function of the kidney. The factors which govern the filtration rate at the capillary beds are total surface area available for filtration, and this is a normal physiological facts. The larger the surface area, the more the filtration, and as you know, the glomerular surface area is very large. And the second factor is the membrane permeability, and this is the greater the permeability, the more the amount of the substance filtered. The last is the net filtration pressure. And as you know, the hydrostatic pressure in the glomerular capillary, as I mentioned, is 60 mm mercury, and this is sufficient to cause a tremendous amount of the plasma fluid to be filtered into the glomeruli. Here is the relation between the different Starling force which govern the filtration at the glomeruli. To clarify this to you, we had 4 Starling force in fact. 2 oncotic and 2 hydrostatic. The glomerular capillary, which is red in color, had hydrostatic pressure 60 mm and tend to move fluid out, and had oncotic equal to 32 and tend to move fluid in. In every area, the hydrostatic tend to push fluid outside the compartment, while the oncotic, which depend on the protein, tend to suck or to move fluid inside the compartment, as you see here. The Bowman capsule also had hydrostatic pressure and had oncotic pressure. The hydrostatic pressure, which is represented here by Cp, here is the hydrostatic pressure represented by Cp. This hydrostatic pressure of the Bowman capsule is just what? Is just 18 mm mercury, and it tends to act against filtration. The next pressure which is present in the Bowman is the oncotic pressure, and it is not mentioned in this picture because there is no albumin in the filtrate, and because there is no albumin in the filtrate, the oncotic pressure of filtrate is 0. So this equation show or not show to you the oncotic pressure in the Bowman capsule. Now, benign glomerular capillary hydrostatic pressure tend to push fluid out from capillary into the Bowman, and it is 16, while the other 2 force, the oncotic capillary and the hydrostatic Bowman, act against filtration. So 60 minus 32 minus 80 will be 10, and this 10 net filtration pressure. Therefore, the net force in the glomeruli in favor of filtration, and the fluid will be filtered from the glomeruli into the Bowman capsules. Autoregulation of renal blood flow and the GFR. A number of factors will regulate renal blood flow and the GFR. One of them is the myogenic mechanism. What we mean by myogenic mechanism? This depends on the physiology of the smooth muscle which is present in the wall of afferent arterioles. When blood supply to the kidney increase, afferent arteriole blood flow will be increased, and the smooth muscle which is present in the wall of afferent arterioles will be stretched. This will lead to contraction of smooth muscles, constricting the afferent arterioles, decreasing the blood flow to the glomeruli, and returning the situation to its normal state. When, I will repeat it to you, when the blood supply to the kidney increased, the blood flow in the afferent arteriole will be increased, and the decreasing of the blood flow in the afferent arterioles will be stretched the smooth muscle which is present in the wall of the afferent arterioles. A stretching of the smooth muscle in the wall of afferent arterioles will lead to vasoconstriction of the afferent arterioles, decreasing the blood flow to the nephron glomeruli, and returning the situation to the normal state. The second one is the tubulo-glomerular feedback, and this is depend again on the juxtaglomerular apparatus. Juxtaglomerular apparatus. As I mentioned, this epithelial cell lining the initial segment of the distal convoluted tubules, this is distal convoluted tubules, is known as macula densa. Macula densa are sensitive for glomerular flow, for filtrate flow, for sodium and chloride load. When the blood supply again to the nephron increased, the filtration is increased, and the flow rate at the distal tubule will be increased. The concentration of sodium and the chloride will be increased. Increasing of sodium and the chloride concentration will be sensed by macula densa. Macula densa by secreting renin and sending direct signal to the afferent arterioles, leading to the constriction of the afferent arterioles and the decreasing of blood flow to the nephron, and returning the situation to its normal state again. I will repeat it again to you. Tubulo-glomerular feedback mechanism depend on the juxtaglomerular apparatus. Number one, when the blood supply to the nephron increased by afferent arterioles, the glomerular filtration will be increased, and the increasing of the glomerular filtration increase the flow rate in the tubules. Increasing of the flow rate in the tubules will be increased the load of the sodium and the chloride reaching the distal convoluted tubules. This is distal convoluted tubules, and this will be sensed by the macula densa. Macula densa, when the load of the sodium and the chloride increase, release renin and also send paracrine signal to the afferent arterioles, leading to vasoconstriction of the afferent arterioles and returning the fluid to its, or the flow to its normal situation. There are a number of hormones and other factors again which regulate the renal blood flow, and these are the sympathetic nervous system and the angiotensin II. Sympathetic nervous system and the circulating catecholamine produce vasoconstriction in the afferent arterioles and in the glomeruli and the efferent arterioles, leading to decreased renal blood flow and the GFR. Sympathetic nervous system and the circulating catecholamines is a potent vasoconstrictor, leading to vasoconstriction of all arterioles and the glomeruli, decreasing renal blood flow. In fact, it is main effect on the arterioles. The glomerular capillary contain not much adrenergic receptor, so Scientifically speaking, the effect will be on afferent arterioles and efferent arterioles, and this will cause a decrease in GFR and a decrease in renal blood flow. Angiotensin is a potent vasoconstrictor, as I mentioned. It has some sort of effect different from the sympathetic nervous system. In small and moderate dose, angiotensin 2 cause more vasoconstriction in efferent, than in afferent. Angiotensin 2 in normal, small or moderate dose cause more vasoconstriction of the efferent than afferent, leading to decreased renal blood flow but maintain GFR. How? When the effect on the efferent arterioles is more than it is effect on afferent, the renal blood flow maintained to some extent, but the output is decreased, leading to increased blood volume in the glomerular capillary. Increasing of the blood volume in the glomerular capillary increase hydrostatic pressure and tend to maintain GFR. So, angiotensin 2 decrease blood flow to the glomeruli, similar to sympathetic nervous system, but it maintains GFR, and this is essential in keeping function of the kidney under certain critical